The cost of lifting 1 kilogram of payload from Earth's surface to low Earth orbit has fallen dramatically in the era of reusable launch vehicles. SpaceX's Falcon 9 rocket, using recovered and reflown first-stage boosters, has reduced the price to approximately $2,000 per kilogram, a reduction of roughly an order of magnitude from the Space Shuttle era. The Starship system, if it reaches full operational reuse, is designed to push this figure toward $100 per kilogram. Even at $100 per kilogram, getting material to orbit is expensive in a way that fundamentally constrains what humanity can do in space. Building a large space station costs as much as it does primarily because of the cost of lifting its components. Sending humans to Mars costs what it does primarily because of the propellant and hardware that must be lifted against Earth's gravity. The space elevator concept proposes to solve this problem at a more fundamental level, not by making rockets cheaper, but by eliminating the need for rockets altogether. A cable extending from Earth's equator to an altitude of approximately 35,786 kilometers, geostationary orbit, where an object circles the Earth once per day and therefore appears stationary relative to the surface, would allow cargo to be lifted along the cable mechanically, like an elevator, using electrical power rather than chemical propellant. At geostationary altitude, the outward centrifugal force of rotation balances gravitational pull. A cable attached at the equator and extending to geostationary orbit would remain taut under tension, like a stone on the end of a string being swung in a circle. Cargo climbers moving along the cable would accelerate as they rise, gaining orbital velocity gradually from the rotation of the Earth rather than all at once from combustion. At geostationary altitude, they could be released and would remain in orbit. Cargo released above geostationary altitude would have more than orbital velocity and would fly outward into the solar system, providing a free launch to anywhere in the planetary system. The energy required to lift a kilogram to orbit via a space elevator, rather than via rocket, is determined purely by physics and the efficiency of the electrical motor. Estimates consistently place it below 100 kilowatt-hours per kilogram, an energy cost at commercial electricity prices of perhaps $10 per kilogram. The cost of reaching orbit could, in principle, fall from thousands of dollars per kilogram to something comparable to intercontinental freight shipping. The engineering problem is the cable. A space elevator cable must simultaneously satisfy requirements that no known material comes close to meeting, until potentially carbon nanotubes. The cable must support its own weight across 36,000 kilometers while also supporting the weight of climbers and cargo moving along it. The tension in the cable at geostationary altitude, the point at which the cable's own weight below and the centrifugal pull of the cable above are greatest, sets the fundamental material requirement. The cable must not break under this tension. The ratio of a material's tensile strength to its density, called specific strength, determines whether a cable of a given material is even theoretically possible for this application. Steel, the strongest structural material in widespread use, has a specific strength far too low. The cable would need to be so thick at the midpoint to support the weight of the cable below it that would weigh more than any conceivable counterweight or anchor system. Even ultra-high-strength steel doesn't get close. Carbon fibers, Kevlar, and other advanced composite materials are closer, but still insufficient by roughly an order of magnitude. Carbon nanotubes, cylindrical structures of carbon atoms arranged in a hexagonal lattice, first characterized in 1991, have theoretical specific strength, values that would be sufficient for a space elevator cable with margin. A single-walled carbon nanotube has a theoretical tensile strength of approximately 100 gigapascals, compared to steel's roughly 1 to 2 gigapascals. The specific strength advantage is enormous. The problem is the gap between theoretical properties and practical reality. Carbon nanotubes can currently be manufactured in lengths measured in centimeters. The space elevator cable needs to be 36,000 kilometers long. The path from centimeters to 36,000 kilometers passes through engineering challenges that have not yet been solved and that some researchers believe may be fundamentally difficult in ways that are not simply a matter of scale. The properties of carbon nanotubes at the nanoscale are remarkable, but the properties of a macroscopic cable made from carbon nanotubes depend on how individual nanotubes are connected to each other, how the load is transferred from one nanotube to the next across a joint or overlap. The inter-tube connections in current carbon nanotube fibers and composites are much weaker than the nanotubes themselves, and the practical specific strength of macroscopic carbon nanotube materials is currently a small fraction of the theoretical nanotube strength. Researchers working on this problem have made steady progress. The specific strength of bulk carbon nanotube fibers has improved significantly in the last decade, but the gap between current practical performance and the requirement for a space elevator cable remains substantial. The International Space Elevator Consortium, the primary professional organization coordinating space elevator research, has tracked this progress and maintained assessments of what additional advances are required. The general conclusion of serious researchers in the field is that the physics of a space elevator is sound and that the material science challenge is real, but not obviously impossible. It requires advances in nanotube synthesis, alignment, and inter-tube bonding that are the subject of active research, but that have not yet been achieved. Beyond the cable material, a complete space elevator system faces additional engineering challenges that are significant but more tractable than the material problem. The anchor point at Earth's equator must be located in international waters. The equatorial regions are politically complex, and a facility of this strategic significance sitting on national territory would create obvious tensions. A floating ocean platform, similar in concept to the sea launch platform used for commercial rocket launches, is the most commonly proposed solution. Such a platform would need to be the largest offshore structure ever built and would require active position management to maintain alignment with the cable above. The counterweight above geostationary altitude, the mass that keeps the cable taut by providing centrifugal pull, could be an asteroid maneuvered into the appropriate orbit or a purpose-built station. The counterweight must maintain its position and provide sufficient outward pull to keep the entire cable under tension. The climber vehicles that would move cargo along the cable require a power delivery system. Climbers powered by onboard fuel would be self-defeating. The fuel would add to the mass that must be lifted. The proposed solution is power beaming, delivering energy to the climbers via laser or microwave beam from the surface. But the efficiency of power beaming over the distances involved and the engineering of receiving systems on the climbers require further development. The cable must also be protected against debris. Low Earth orbit contains significant quantities of space debris, defunct satellites and fragments from collisions, that move at velocities that would sever a cable on contact. The cable would need to be maneuvered to avoid predicted collisions, which is possible for a tethered cable through wave propagation along the cable's length and would ideally be self-repairing for smaller impacts. The transformational potential of a working space elevator is the reason serious engineers and space agencies continue to study it despite the material challenges. At $10 to $100 per kilogram to orbit, the economics of space development change entirely. Solar power satellites, large arrays of photovoltaic panels in geostationary orbit, transmitting power to Earth via microwave, become commercially viable. The cost of raw materials for in-space construction falls to the point where large structures are buildable. The cost of sending humans to other planets falls to the cost of the life support systems and transit vehicles, not the cost of lifting them off Earth. The space elevator represents a transition from the rocket paradigm, in which accessing space requires burning enormous quantities of propellant in a single violent event, to the infrastructure paradigm, in which space is connected to Earth by a permanent physical link that can be traversed with the energy efficiency of terrestrial transportation. The carbon nanotube needed to make it real is, as of now, between 1 and 2 orders of magnitude away from practical existence in the required form. Whether it gets there is a question of materials science research, manufacturing investment, and time. The physics is not the obstacle. The cable is the obstacle, and the cable is a solved problem waiting on a material.